My name is Muaz Ahmed Jan, and today I will be presenting my final year project, which is titled to be Design of a Heating System of Compressor Test under great supervision of Professor from the Spuy. Engineers globally are in pursuit of the following goals: reducing carbon emissions, making power generation processes efficient, and also ensuring power requirements are met. Microgas turbines and turbomachinery in general is contributing immensely to ensure that the stated goals are achieved. For this very reason, small gas turbines have gained interest in both civilian and military applications. There is ongoing research at the University of Stellenbosch to enhance the design of microgas turbine components and improve efficiency. For this project, my focus is mainly on the centrifugal compressor test facility, which can be seen in Figure 1. In the facility, a turbocharger is used to drive a test compressor using compressed air. The purpose of the facility is to accurately measure the performance of a centrifugal compressor. Objectives of my project included detailed theoretical analysis needed to be performed on the test facility, a heating system needed to be designed which will be able to provide enough energy for the test facility to reach speeds in order of 120,000 rpm. Conceived design needed to be manufactured and assembled. Lastly, design must be tested. In motivation, the test facility was initially designed to be operated with cold air. The use of cold air raised two major issues. Firstly, in order to achieve higher speeds, the facility must be operated at high pressures. Secondly, during operation, turbine extracts enough energy out of the air which causes air temperature to decrease below 0 degrees. This results in frost build-up on the diffuser and the impeller, consequently decreasing the efficiency and also lifespan of the turbocharger. For the theoretical analysis, I was given the specification of a new design of a compressor. Therefore, a detailed theoretical analysis was done on the facility in order to determine how much power is required by the compressor. Also, the inlet temperature of the turbine had to be calculated to ensure that required power is delivered. Layout of the facility can be seen in Figure 3. Theoretical analysis findings are listed in Table 1. It was found that the turbine needs to deliver 188 kilowatts of power to drive the compressor. In order to obtain this power, inlet temperature of the turbine must be around 842 Kelvin, along with the mass flow rate of 0.45 kg per second. For combustor design, previously a heater with heating elements was designed for similar purpose with a power output of 36.75 kilowatts, and it was recommended that a heating system with a higher power rating is required. After in-depth research, Combustor was considered to be a viable option. This choice was further motivated by Council for Scientific and Industrial Research, CSIR. In fact, I was given the specification of the combustor, which are listed in Table 2 with a rough sketch of the combustor. The rough sketch was converted into 3D models and final product was manufactured and assembled. Before conducting final tests on the combustor, a preliminary test was done to inspect the viability of the design and to identify if there are further modifications which needed to be implemented. Test setup can be seen in Figure 4. For the final test, instruments listed in the Table 3 were utilized to measure the respective parameters which will ensure the controllability of the combustor. Test was conducted in the combustor test cell shown in Figure 5. All the test trials were examined on the basis of the following criteria: noise level, stability of the flame, color of the flame, and pulsation effect. Results were categorized into two categories: frequent observations and notable findings. Frequent observation includes occurrences which were noticed in all the test trials, which includes the following: instability of the flame at the startup, initial dripping of the fuel from the outlet of the combustor, flame reaching stability as fan speed is increased. Figure 6 shows the frequent observations. Special attention was given to the initial dripping of fuel as it is a serious safety hazard. Three speculations were made regarding this occurrence. Firstly, leakage in the fuel pipeline upstream of the combustor. Secondly, fuel nozzle is not atomizing the fuel properly. Thirdly, the position of igniter is far from the nozzle, which results in a delay in ignition, furthermore cause the fuel to accumulate. Notable findings include occurrences which were distinctive to different set of test trials, which include the following. Firstly, flame losing its anchor, which results in flame protruding outside of the flame tube. Secondly, lean combustion was observed. Thirdly, rich combustion was also observed. Table 4 summarizes each finding with its respective mass flow rate range and air-fuel ratio. With regards to flame protruding outside of the flame tube, this phenomenon was referred to as flame losing its anchor, which occurred at high fuel flow rates. After this occurrence, further increase in airflow rate causes the flame blowout. It was also observed that noise level of the combustion decreases significantly. This phenomenon can be seen in figure 9. A stable blue flame was achieved, which is referred to as lean combustion. It can be seen in figure 10. Also, rich combustion is shown in figure 11. It depicts a stable flame with yellow-orange color. With regards to the instabilities, throughout testing trials, pulsating effect was noticed in shape of inconsistent noise level and abrupt change in color of the flame. Following reasons were thought to be the cause of instabilities: inefficient fuel atomization, insufficient mixing of fuel and air, malfunctioning of the swirler due to manufacturing defects, and non-continuous ignition system. In conclusion, safety concerns enforced limitation on the testing of the combustor. We had to use combustor test cells for the testing of the design instead of centrifugal compressor test rig, for which the combustor was actually designed. Combustor test cell was limited to its airflow rate, hence the design parameters were not met. Despite of all the limitations, the design was proven to be functional. Lean combustion was achieved, but due to instabilities, it could not be sustained for a long period. To further improve the design and its controllability, following recommendations were suggested. Firstly, variable fuel nozzle must be used for the design to ensure effective variation of fuel flow rate. Secondly, a flow rate control valve is recommended to directly measure an accurate flow rate of the fuel. Thirdly, as mentioned earlier that the position of the igniter can be a possible reason for initial dripping of the fuel, it is recommended to use an igniter electrode rather than a spark plug, as spark plugs are restricted by its length. A provision must be made in the combustor so that the accumulation of the fuel in the outer casing can be prevented. This provision will make sure that the fuel found in the combustor's outer casing is drained. Lastly, a feedback control must be implemented to achieve better control of the combustor's stable operating point. I will end my presentation with a video clip which is one of the test trials on the designed combustor.